One problem. Okay, so some of you actually noticed some of the difference, but some of you, I'm on the 9-2 homework. Yeah, problem number 6. The 9-2 homework, problem number 6. Some of you just tried to answer it. And if there is an answer to the problem that's written there, there would have to be 2 answers. Because when you expand to the 7th power, this is problem number 6, when you, on 9.2, when you expand to the 7th power, there are actually 8 terms. Now think about that. Remember, you just look at your coefficients. Or your powers on x. If you're going to the 7th power, you have x to the 7, 6, 5, 4, 3, 2, 1, 0. And if there are 8 terms, then there isn't a middle one. You could say, okay, these are both middle terms, but there isn't a middle one. So on my paper, and now I have fixed it on the master copy, but it's too late for you, I'm so sorry. X plus y to the 8th. Now we can find the middle term. Because if it's to the 8th power, there will be 9 terms. Think of your exponents, x to the 0, or x to the 8th, all the way down to x to the 0. So there'll be 9 of them. So which one will be the middle one? Well, I don't know. Let's see. We're going to have x to the 8, 7, 6, 5, 4, 3, 2, 1, 0. There are all the terms. So the middle one will be right here. So basically, now that I've changed the problem, what I'm asking for is the middle term, the x to the 4th term of x plus y to the 8th. Okay, now we've already figured out the power on x is going to be 4, which automatically means the power on y is going to be 4, because they have to add up to 8. Now we're going to change the problem. And the only thing I'm missing is my coefficient, which I could either get from Pascal's triangle, or since I don't have it up here, I could say, okay, this coefficient would be 8C8. 8C, 7, 6, 5, 4, 8C4.
Yeah.
And then I can go to my calculator. 8C4, what is it? 70. So the middle term is that. Okay, so I'm sorry some of you were concerned about that. I totally get it. I mean, there is no answer to the question I asked. But got it now? Got that fixed. Okay. Now, I need to correct something I did yesterday. I want just to, I don't go for excuses, but I did have a nose full of shaving cream, and I was a little spastic. So I need to go back and look at, well, I have to start with A, because I have to. So I'm going to go back to our notes that we did yesterday. Problem 6A. And this is part 9.3. So 6A, we're back to this. This part was all okay. We had jar A and jar B, or jar A and jar B. And of course we had a 1/5 chance with either one, 1/2 chance with either one. And then we were picking a cookie, and it was either a chocolate chip cookie or a peanut butter cookie. And our probability of a chocolate chip cookie from jar A was 1/2, and our probability was 1 and 0 here. So we did all that part right. That part was all okay. It was part B that I messed up, because part B says, what is the probability, find the probability of jar A given chocolate chip cookie. Okay, I had that turned around. the probability of jar A, given that I got a chocolate chip cookie. So given that I picked a chocolate chip cookie, what's the probability it came out of jar A? Okay, so here we go. The formula for this called conditional probability is the probability of both. So both A and C divided by the probability of C. I don't think that's what I did yesterday. That's what I need to do. Okay? So, what is the probability of A and C? So both of these. Jar A and chocolate chip, this would be 1/4. So my numerator is 1/4. Now that's the same because both of these, no matter what order things are in, you're gonna have those. Now what's the probability of getting a chocolate chip cookie? The total probability. Well, this is one way to get a chocolate chip cookie, right? But isn't there another way to get a chocolate chip cookie? And what's that probability? 1/2? 1/2 times 1? So what's the total probability of getting a chocolate chip? If I can get it this way or this way, what am I going to do with those two numbers? Add them up. Fundamentally, two things happening at the same time. A and C is multiplied. If it's this chocolate chip branch or this chocolate chip branch, then I add. So what is that, 3/4? So what's the answer to the question? 1/3. There we go. There's the right answer. All right. So to make up for that screw up, which I know caused Zoe and I don't know how many others great anxiety.
No way.
I made you a brownie. These are also to celebrate the wonderful achievements of the theater program. And they're wonderful. Okay. All right, so I think now that I have fixed all my mistakes. Okay? Zoe, we all good now? All right. Number eight, here we go. We roll a fair die 4 times. Find the probability that we will roll all 3s, okay? Now there's more than one way that you can do this, but the easiest way I think is to think about this as kind of like one of those X plus Y expansion problems. Because when you roll a die, it's binary. You're either going to get a 3 or you're not going to get a 3. In this problem, that's why I'm interested in 3s. So I'm going to get a 3 or I'm not going to get a 3. What is the probability that I will get a 3? 1/6. And the probability that I don't get a 3 is 5/6, right? All right, so here we go. I'm going to roll that die 4 times. And in problem A, I want them all to be 3s. Well, I'm going to show you how we're going to approach these other problems, but you could definitely approach this one by just saying 1/6 times 1/6 times 1/6 times 1/6. Since all the rolls are going to be exactly the same, then you can just multiply that probability 4 times. Now, from a more universal aspect, so how we're going to have to do it if we want 2 3s, that's not going to work if you just want 2 3s. So what I'm going to do is say, okay, I have 4 rolls, and all 4 of them are going to be 3s. So of my 4 rolls, I'm going to pick 4 to be 3s. All 4 are going to be 3s. The probability of a 3 is 1/6. The probability of not a 3 is 5/6. I want 4 3s and none of the others. Now, this will be the same answer because 4C4 is 1, and this is 1. Basically, it's 1/6 times 1/6 times 1/6 times 1/6. There's nothing wrong with that strategy on this particular problem. Okay? Similarly, no 3s. Well, if I'm doing it kind of formally, like in a universal way, I'm going to say, okay, if I went no 3s, that's going to be 4C0, 1/6 to the 0th, and 5/6 to the 4th. Now, does that setup at least make sense to you, even if you didn't do the problem that way? Does that make sense? Okay, that's the same. This is 1. This is 1. So this is the same as saying, okay, I'm going to roll that 4 times. 5/6, 5/6, 5/6, 5/6. Now, exactly 2 3s. Now here's the deal. If you're rolling exactly 2 3s, could it be the first 2 rolls? Could it be the second and the 4th roll? Yeah. The order of the 3s doesn't make sense. It doesn't matter. I don't care when I get them. I just know that of my 4 rolls, I need to pick 2 of them to be 3s. The probability of a 3 is 1/6, and I want 2 of those. And the probability of not a 3 is 5/6, and I also need 2 of those. Now, this problem cannot be done by saying 1/6 times 1/6 times 5/6 times 5/6. Because if you do it that way, what are you saying? Literally, what are you saying? My first roll is a 3. My second roll is a 3. And then I get 2 not 3s. And that is not what this problem says. Is that part of the answer? Yeah. So if you absolutely insist on doing it this way, you can, but then you have to turn around and do all the possibilities. You see what I'm saying? And who wants to do that when this will handle it for you? All right, let's type this in, make sure we can get the right answer.
So it is the right way to do it?
Well, this is the best way to do it. Yes, yes. This is not right. Now, with these 2, you could have done it this way because all the numbers were the same.
Yeah.
But not with
Oh,
this
this
one.
is B?
This is C.
Wow.
No, this is C. All right, and I'm typing it in carefully.
No 3s at all.
Okay, so what I got was 0.1157. Anybody else get that? So you have about 11.5% chance of doing that.
Not yet.
All right, here we go, number 9. 5-card hand is dealt from a standard deck. What is the probability of the given event? All right. Now, first of all, it's a 5-card hand. It's a 5-card hand. So the probability is going to be a fraction. What's going to be in the bottom of that fraction? Remember, probability, the denominator is the total. All right? So what's going to go in the bottom? Bingo, 52C5. Why is that going in the bottom? How many cards are in the deck? 52. How many am I picking? 5, period. No restrictions. I want all the possible hands in the deck. That's the denominator. all the possibilities. Now, what's the numerator? At least one king. Okay, stop a minute. This is a 5-card hand. What does at least one king mean? One king, or 2 kings, or 3 kings, or 4 kings? I can do it this way. Remember what we talked about the other day? What did we talk about the other day? Sometimes it's easier to do what? I thought we talked about this.
The total minus the negatives.
Yeah, so it's easier instead, this is literally what the hands that I want. It might be easier to take 100% minus the probability of what I don't want. What is what I don't want? What's the only thing I don't want? A hand with no kings. So a hand with no kings would look like what? If I wanted to guarantee I got no kings, what would that look like?
Is that 48 C5?
48C5. Now, where did she get 48C5? She took the kings out of the deck. If you want to guarantee that you're going to get no kings, pull them out. Right? Now you're not going to get any because you took them out. There's 48 cards left. So what is this representing? This fraction right here is the probability of no kings. And don't I want everything else? So what am I gonna do? I'm gonna take this fraction, whatever it is, and subtract it from 1. So this is gonna be some fraction, like we got 11.5% here. So it's gonna be 1 minus whatever that decimal is. That's gonna be your probability. So 1 minus 48C5 divided by 52. I got my total answer, my final answer, I got 0.341. Anybody else get that?
Yeah, you saw it.
So there's about a 34% chance that you'll get a hand with at least 1 king in it. If you want to do it this way, you absolutely can. But let's look at what one of these, for example, looks like. What would 1 king look like? The hands for 1 king. 4C1 times 48C4. Why? How many kings in the deck? 4. How many do you want? 1. How many non-kings in the deck? 48. How many do you want? 4, because it's a 5-card hand. So this would be that one. Or then you would do the same thing here, and here, and here. And that would be your numerator. And when you took that and divided it by this, you would get this answer right here. So you're either gonna have to do all the cases that you want, or you're gonna do 1 minus the case you don't want. And these can get a little, you have to think. You have to think, for sure. All right, let's look at number 10. All right.
God,
Are we skipping 9B?
Oh, no, I didn't mean to. Thank you, Sammy. A hand will be a full house, any 3 of one kind, and a pair of another kind. Okay, what's the probability that happens? Well, my denominator hasn't changed. Would you agree with that? It's still a 5-card hand. So apparently I want to get 3 of a kind and 2 of a kind. All right, so let's break it all the way down. Let's be very specific. Let's say I want 3 queens and 2 5s, okay? That would be a full house, right? I don't play cover, okay, play poker, but I guess that's what it is. Now, let's just do that case. 3 queens and 2 5s. So what did you say?
4C3.
4C3 and, so times 4C2? Does that make sense to you? All right, well, what if I wanted 3 10s and 2 6s? Would it be the same thing? And all the different things, right? So what I really don't want to do all the individual ones. What I want to do is figure out how many of those there are. Tess? No, your numerator is what you want. And if you want queens, then you're gonna pull the queens out and you're gonna say 4. There are 4 queens and you're gonna pick 3 of them. Now, all the possibilities are in the denominator. So the queens are down here for sure. But up here, I'm very specific. That's what I want to have happen. Lucy?
So in the 52C5, the 5 is the amount of cards, like 3 queens and 2 5s.
A 5-card hand. Anytime it's a 5-card hand, that's gonna be your denominator. I don't know what you're doing. That's the total number of hands there are in the deck. 5 cards. Okay, so what I want you to think about is, to do this full house thing, okay, how many different kinds of cards are in the deck? 13? Aren't there 13 different kinds? Tell me if I'm crazy, I think I'm right. There's 13 of them? Okay, so if there's 13 different cards, different kinds of cards, to do a full house, I need to pick 2 of them. Would you agree with that? So then I gotta ask myself, does the order, like here, I picked queens and 5s. I could pick 10s and jacks. Does the order I pick them matter? In other words, is this gonna be a 13 C2 situation or a 13 P2 situation? What do you think?
The order doesn't.
Okay, I've heard both. He said permutations, which means order matters. You said order doesn't matter. So let's hear your argument.
3 queens and 2 5s is different from 3 5s and
2 queens.
Yeah.
Perfect. He is picking a different number of each kind. Okay? So if he picks, his point is, these 2 are different things. They're the same 2 sets of cards, but they're different.
So like in the directions, it says 3 of a kind and then a pair of a kind, and we need to stick to that order. Because that's how it's written and that's how you're expecting it, right? Like we can't do a pair and 3, because then that would be a computation, right?
No, I don't think that order matters. That kind of order, I don't think matters. I think what matters, why the order matters is, if I'm picking queens and 5s, I could pick 3 queens and 2 5s, or 2 queens and 3 5s out of the same pile of cards. And that is different. That those hands would look different. Would you agree with me? Yeah. Now, if I were picking 2 of each, then would order matter? No. But since they're different amounts, that's gonna matter. It's okay, I believe you. Be safe and smart. Oh wait, stop. This is not to go to a hair appointment or something, right?
No, it's track pictures.
Oh. Okay. During the day, really? Okay, all right. So, this is the specific probability of 3 queens and 2 5s. I am gonna take this guy and multiply him by 13P2. Because there are 13 different kinds of cards, for me to pick, and I have to pick two at a time, 2 kinds at a time. The order I choose them matter, so that would be the answer. Now, your only other alternative, guys, is to do this over and over and over again for every possible setup, which would be a lot. So you gotta think about this like that. There are 13 kinds and you're picking 2 of them. All right, let's see what that is, by the way. You have to pick 2 different kinds of cards. There are 13 kinds of cards, but you have to pick 2 kinds. So do what the problem wants. That's a P. I have a feeling this is going to be a very small number. What'd you come up with? That's what I got, .0014.
Yeah.
So percentage-wise, that's like a 0.1% chance. For you. Okay.
A fur.
All right, Sammy, is that good? Okay. All right, now number 10. Here we go. We want to finish this if we can. Number 10. Using Venn diagrams. Okay, let's do some directions. A, B are events in the sample space. The probability of A is 0.7. The probability of B is 0.4. And the probability of A and B is 0.2. Now, it tells me the directions to use a Venn diagram, and that sort of makes sense, because the minute they told me that A was 0.7 and B was 0.4, somewhere there's going to be some overlap, right? So here's my A, here's my B, here we go. Do not put 0.7 right here. That is not 0.7. The whole A circle is 0.7. The only number I can put in there right now is this one, because that tells me the overlap is 0.2. The A and B is 0.2. The minute I do that, then I can tell you what this is.
Pardon this interruption. At this time, all boys golf members should go to the Welch Activity Center for their team pictures. Again, all boys golf members should go down to the Welch Activity Center for team pictures. Thank you.
Okay, so what's this part right here? 0.5, because the whole wall is 0.7. What's this part right here? 0.2, because the whole wall is 0.4. Okay, now wait a second, something's missing. Because these add up to 0.9. Where's the other 10%, 0.1, where are they? They're out here. So if you think about this as A's are like apples and B are like bananas, then there's 10% of the people that don't like either one. Okay, so now let's answer the questions. Draw a Venn diagram, so we did that. Find the probability that A occurs, but B does not. Now the way that will be written, the way that problem will be written, find the probability that A occurs and B does not. So that's the way that will be written. The probability of only A, basically. A and not B. Okay, so what is that? What's the probability of A and not B? 0.5. Find the probability that B occurs, but A does not. Okay, so that would be the probability of not A and B. So what would that be? This 0.2 right here. And then neither A nor B. So the probability of not A N not B, and that would be our point one. I gotta talk with Mr. Shaddy. I'm not gonna, well, I guess we can do this for practice. I don't know if we're gonna spend time on this independence thing or not, but this is good practice for us. They're telling us, check to see if this is true. Check to see if this is true. So in other words, the probability of A given B, what is that? What is the probability of A? And do those two things match? Okay, so let's do this. What's the probability of A given B? Well, that's our conditional probability. That's A and B over the probability of B. So that's what this always means. The probability of both, A and B, the probability of both, over the probability of what's given, which in this case is B. All right, let's evaluate that. What's this one? The probability of A and B is 0.2. And the probability of just B is 0.4. So this side of the equation is basically 1/2. Now, what's the probability of A? 0.7. Are they equal? No. So therefore, these events are not independent. They're not independent events. But again, this is good practice for us to do. I'm just not sure why we didn't mess with the independent, so I don't want to get all hung up in that vocabulary right now.
So how did we, oh, sorry.
That's the way it's
Yeah, how did we figure out that A slash B
That's
gives you?
A given B.
So how did we?
This is the order of it. We talked about that yesterday. Yeah, I actually read that right yesterday.
This is A, A on the bottom.
Yeah. All right,
This is B here. Look.
here we go. Listen, I'll make you a deal. We get through these last two problems and I'll go shut up, okay? Good deal, that's a good deal. All right, here we go. If it rains tomorrow, the probability is 0.8 that John will practice his piano. If it does not rain tomorrow, there is a 4% chance that John will practice. Suppose that the chance of rain tomorrow is 60%. What is the probability that John will practice his piano lesson? Okay, now there are a couple different ways you can do this. And here's what I'd like you to think about. Tomorrow, it is either gonna rain or not. Would you agree with that? And the probability it's gonna rain is 0.6. So the probability it won't rain is 0.4. Now, whether it rains or not, John is gonna play the piano or not. So, if it rains, he's either gonna play or not play. If it doesn't rain, he's either gonna play or not play. Would you agree with that? Now, if it rains, so right here, raining, if it rains, the probability is 0.8 that he will play. So what's the probability he won't play? 0.2. If it doesn't rain, the probability he'll play is 0.4, which means he won't play 0.6. Now your job is to find the probability that he's going to play tomorrow. Well, kids, can't he play here or here? Aren't there two ways that he can play? So we're gonna calculate this, that is rain and play. So rain and play would be 0.48. Rain and play. Rain and, or excuse me, not rain and play is 0.16. And since he can do it either this way or this way, what are you gonna do with those two numbers? We're gonna add them together, and that would be 0.64.
Yeah.
Now, using the same thing, you could say, what's the probability he won't play? Right, using the same strategy. Yeah, obviously we won't play. All right, are you okay with that? Now, one question, it's all perfectly easy when I'm standing up here doing it. I mean, those really are easy. But if you are left on your own to do a problem like this, whatever the ultimate question is, they always give you lots of stuff. You could have even more coming off of it, some more branches, but they always ultimately ask a question. The question that's asked is, what's the probability that he'll practice his piano? If you're gonna set up a tree diagram, that's what this is called, if you're gonna set this up, whatever the question is the bottom line. So in this problem, we had conversation about rain and piano. Since the question is about piano, we're gonna have piano on the bottom and rain on the first branch. Does that make sense to you? If you have to do it on your own and you're not sure, that's how you know how to set it up. All right, last one. Here we go. Suppose Michael makes 90% of his free throws. Okay? So the probability of a free throw is 0.9. The probability of not a free throw then is 0.1. He's gonna shoot 20. What is the probability that he makes all 20? Now, don't get all hung up about that stuff. Here's the deal. I step up to the line to shoot a free throw. I either make it or don't make it. Is that gonna impact my next shot? No, I'm gonna make it or not make it. Now, what they're saying is, okay, if I miss the first 7, then I probably have a bad mindset and I'll probably miss the 8th. But they're telling us it doesn't matter. I'm just gonna shoot 20 of them, and this probability doesn't impact this one. I have the same probability each time. So here's the question. What's the probability I'll make all 20? Kylie?
It's like 1/2.
Okay, now, you're very close, but the probability of me making it or him making it, now, it will be different if it's me or him, but the probability of him making it is 90%, not a half. He's got a 90% chance of making it. So you have the right idea, but it's not 1/2, it would be 9/10. So Kylie says, could I just take 0.9 to the 20th? And the answer is yes, because he's making every single one of them. So it's 0.9 times 0.9 times 0.9. Now, again, formally, 20C20, 20 shots, making them all, 0.9 to the 20th, 0.1 to the 0. This is the formal way of doing it. But Kylie is okay because we're making them all. What is the probability I'll get exactly 18? That's gonna be 20C18. This is how many I'm trying. I'm trying 20 times. I'm gonna make 18 of them. Do I care which 18? That's why it's a C. 20, let's take an 18. Then I have my 0.9 to the 18th, because I'm making 18 of them. And I'm gonna have my 0.1 to the 2nd, because I'm missing 2 of them. Okay, Kylie, you see that setup makes sense to you? Yeah. Okay. So this is exactly 18. How am I gonna handle at least 18? This is 18. 18 points. All right. If I have to make at least 18 points, then that means I could get 18. But what else could happen? I could get 19 points, or I could get 20 points. Now, I already did this one, but I'm gonna go ahead and do it again. That's 20C20, 0.9 to the 20th, 0.1 to the 0. Now, again, I'm doing it formally. This is exactly what Kylie said, 0.9 to the 20th, because he's making them all. What's this one? 20C19, 0.9 to the 19th, and 0.1 to the 1st. This is gonna be a number, this is gonna be a number, and this is gonna be a number. And what am I gonna do with those three numbers? I'm gonna add them all up. I'm gonna suggest that you not do them individually and write them down. I'm gonna suggest you just type it all in on your calculator. It will do it. If you type this and then hit plus, and then do this and hit plus, it will do it. If you do each step, you're gonna have round off error along the way. We really wanna avoid that if we can. Okay? Now, what if it said, what's the probability he'll make at least 2?
Do it the other way and subtract.
Do it the other way. Because if you wanna make at least 2, that would be a lot of these cases. So we would take 1 minus the probability of 0 and the probability of 1. Does that make sense to you? If we were to make at least 2? Okay, did you get an answer to this problem?
Oh, me?
Anybody, I don't care. I'd like to get an answer so we know we're all typing it in right.
0.68?
I don't know, I'm typing it in right now. Just a second, I'm going down here in a minute. What'd you get?
6767.
That's what I got.
What did you get?
I got 0.6967.
Oh, wait, I made a mistake. Let me fix something else, if I see a mistake. I can fix it.
It smells like
All right, I'm sorry. Somebody tell me what the answer is. 0.67 something? All right, I'm gonna type it in and make sure that's right, but I won't hold you. I promised I'd be done. I am gonna type that in now and make sure that's the right number. Okay? Now, what we'll do next time